Greetings, everybody. Learning is a hobby here. Today, I want to go over my summary for Chapter 3 in this book here, Topics in Commutative Ring Theory by John Watkins. So that's what I'll do here. So let me bring up my notes. Just bear with me for a second. Why is this working? Okay, so here we go. All right, so we're going to look at prime ideals and maximal ideals in this section. So this is, like I said, this is chapter 3 in the Watkins book. Okay, so we start with some motivation. So how are we to capture the notion of primeness in an arbitrary ring? And the key is divisibility. We talked about primes in section 1.3 in Niven's book, which I posted the video for a couple of days ago if you haven't seen that, so check that out. Anyway, let's do definition 3.1 here. So let m and n be integers. We say that m divides n if n is Rm for some R in Z. And in this case, we write m and then the vertical line n, which is read m divides n. Right, divisibility is mirrored in the ideal structure of the ring Z as follows: m divides n if and only if the principal ideal n generated by n is contained in the principal ideal generated by m. Okay, so note, as long as the numbers in question are positive, the smaller number corresponds to the bigger ideal. If P is prime, then P has the following well-known divisibility property. Again, this is something we talked about in the Niven book in section 1.3. So again, check that video out if you haven't seen that. If P divides AB, then P divides A or P divides B. And note, just be careful. This statement here is not necessarily true for composite numbers, but it's a property of primes. Right, so this fundamentally important divisibility property is equivalent to the original notion of primeness, and it happens to be the one that is most suitable for generalization. So we're going to use that to define what we mean by a prime ideal. Okay, so here's definition 3.2. Let P be a proper ideal of a ring R. Proper means that it's not the entire ring. So he says that here, P is not R. Then the ideal P is prime if for every A, B, and R, A, B, and P implies A and P or B is in P. Right, and then we have an example. Let n be a natural number. Then the principal ideal generated by n is a prime ideal of Z if and only if n is a prime number. And here's my proof. Assume for the sake of contradiction that the ideal generated by n is a prime ideal of Z, but that n is not a prime. Then there are A, B, and Z such that 1 less than A less than n, and same thing for B, and n is equal to AB. So in other words, n is a composite number. Then AB in the ideal generated by n. Then A is an element of the ideal generated by n, or B is an element of the ideal generated by n, since n is a prime ideal. So A equals nk, B equals nm for some k m in Z, implies n divides A or n divides B. However, this contradicts the fact that A and B were both greater than 1 and less than n. Therefore, n is prime. And then we go the other direction, assume n is prime, and that AB are integers with AB in the ideal generated by n. Then AB is nk for some k in Z. Then n divides A or n divides B since n is prime. So A is an element of the ideal generated by n, or B is an element of the ideal generated by n. Therefore, the ideal generated by n is a prime ideal of Z. And that's the proof. Okay, and then we get, once we've defined prime ideals, we can talk about integral domains. One important property of the ring of real numbers, and actually the ring of integers as well, and the ring of rationals too, is that one important property of those rings that's useful in solving equations by factoring is the zero product rule, meaning that if you have two real numbers A and B that multiply to give you 0, then one of them is 0 or the other is 0, or possibly both are 0. Right? The zero product rule is not true in an arbitrary ring, unfortunately. So the rings that have that property are special, and we first need one definition here, and then we'll talk about what we call those rings in a second. This is definition 3.3. Let R be a ring and let A in R. Then the element A is said to be a zero divisor if there is a non-zero element B in R such that AB is zero. And just to note that the zero element is a zero divisor in any non-zero ring. All right, and then we get to definition 3.4. A non-zero ring R is called an integral domain, or often more simply, a domain if R has no zero divisors other than zero. And then we have example 2, which is this statement here. Any field is an integral domain. So here's my proof. Let the ring K be a field. Let AB be elements of K such that A is not zero. If AB is zero, then A inverse times AB equals A inverse times zero. And then we could just associate on the left-hand side. That gives us A inverse times A times B equals zero, because A inverse times zero is zero, which implies 1 times B is zero, or in other words, B is zero. Therefore, zero is the only zero divisor in K, which implies that K is an integral domain. Right? Then we have another statement here to prove in example 3. Let K be a field. Then the polynomial ring with coefficients from the field K is an integral domain. Let's prove that here. Let K be a field, then K is a ring, which implies K of X is a ring. Assume for the sake of contradiction that F is an element of the ring of polynomials, is a non-zero zero divisor. Then there's G in the polynomial ring. G not the zero polynomial, and f of x is given by this polynomial here, g of x is given by this polynomial here, where an is not zero and bm is not zero, because we're assuming these are non-zero polynomials, right? Since fg equals the zero polynomial implies fg has degree 0, that means that the coefficient of the leading term, which should have degree n plus m, is a to the n, a sub n times b sub m. That will end up being 0, which contradicts that an and bm are elements of the field K, which is an integral domain. Therefore, K of x has no non-trivial zero divisors, which implies that K of x is an integral domain. All right. And then we get to theorem 3.1. Let P be an ideal of a ring R, then P is a prime ideal if and only if R mod P is an integral domain. Right? Here's my proof. Let P be a prime ideal of R, and let B plus P be an element of R mod P, where B is a zero divisor. Then there's A plus P in R mod P, a plus p not equal to p, such that a plus p times b plus p equals ab plus p equals p, which implies ab is an element of p, which implies a is an element of p, or b is an element of p. However, a is not an element of p, since a plus p is not p. Therefore, b is an element of p, which implies that R mod p has only trivial zero divisors. So R mod p is an integral domain. All right, and then we go the other way. Let R mod P be an integral domain. Let AB be elements of the ring R, such that AB is in P. Then P equals AB plus P equals A plus P times B plus P. Since R mod P is an integral domain, then either A plus P equals P or B plus P equals P, which implies A is an element of P or B is an element of P, which means that P is a prime ideal because it satisfies the definition. Okay, and that's the proof for theorem 3.1. In order to learn something about R, it may be useful to change the location of the discussion to a ring R mod I instead. And this is a general sort of strategy in not just in algebra, but in a lot of other different mathematical fields, where you take some substructure and mod out by it, and you look at the quotient structure, and it gives you information about the bigger structure. Right? Now we get to maximal ideals. We talked about prime ideals and integral domains. Now we'll talk about maximal ideals and fields. Theorem 3.1 tells us that if R mod I is an integral domain, then I is a prime ideal in R. But what if R mod I is a field? What can we say about I in that case? right? And then we get definition 3.5 of a maximal ideal. Let M be a proper ideal in a ring R, that is, M is not R, then M is maximal if the only ideal properly contained in M, sorry, the only ideal properly containing M is the whole ring R itself. Or in other words, you can think about it this way. M is a maximal ideal of R if for any ideal N where M contained in N containing R implies N is M or N is R. And uh, Watkins says this note below this property here. The above will be our basic strategy for showing that an ideal is maximal. That is, take an ideal N between M and R and show that N is M or N is R. Or alternatively, you can do a proof by contradiction. We'll take an ideal N properly between M and R and derive a contradiction. So we'll do some examples with that we'll see in a minute. Actually, right down here in example 4, we'll do one. Show that the ideal generated by 7 is a maximal ideal of the integers. And here's my proof. Let N be an ideal of Z such that 7 is strictly contained in N, strictly contained in Z, and take N in the set difference of N with the ideal generated by 7. Then the ideal generated by N and 7, sorry, not the ideal, the GCF of N and 7 is 1, right? They're relatively prime, implies that there are mk in Z such that 7m plus nk equals 1. That's by the division algorithm. Implies 1 is an element of N. Since 7n nk is in N. N here is the ideal that I'm talking about, not the natural numbers, by the way. Implies N is R, which contradicts that N is a proper subset of R. Therefore, the ideal generated by 7 is maximal. All right. Example 5, the ideal generated by 6 is not maximal in Z, since the ideal generated by 6 is contained in the ideal generated by 2, which is a proper ideal of the integers. And then we have a statement here, all maximal ideals are prime ideals, which we'll prove in problem 3.9 in the exercise set, so I didn't prove it here. Okay, definition 3.6, let S be a subset of a ring R, then the ideal generated by S is denoted by, it looks like the notation that we've been using for ideals generated by an element, but here it's generated by the entire set S, and is the intersection of all ideals that contain S. That is, the ideal generated by S is the intersection of all ideals containing S. All right, we can also describe the ideal generated by S as the set of all linear combinations of elements of S with weights in R. So, in other words, as this set that I have written here. And the reader's asked to prove this in problem 3.7, so we'll do that in the exercise set. So I didn't bother doing it here. And then another statement here, the reader will also be asked in problem 3.8 to show that the ideal generated by I and the element A is given by that set of elements I plus RA, where I is an I and R is an R. So we'll do that in the exercise set too, so I won't prove that here. I'll do that in the next video. Okay, then we get to theorem 3.2. Let M be an ideal of a ring R, then M is a maximal ideal if and only if R mod M is a field. Right, and this is the last big proof of the section, but there's a couple of examples after this. So here's my proof. Let M be a maximal ideal of R, and I took it for granted that this is true, but after writing up my proof and reading Watkins' proof, I realized I should probably state this explicitly. So the fact that M is a maximal ideal means it's a proper ideal of R, which means that R mod M is not the zero ring. So just that should be clear from the way that we defined maximal ideals, but I figured I might as well state it explicitly here. Okay, so take A plus M in R mod M such that A plus M is not M, then A is not an element of M, which implies that the ideal generated by M and A is equal to R, which implies that Mn plus AB equals 1 for some NB in R, implies AB equals 1 minus Mn, which is an element of 1 plus M, which implies that A plus M times B plus M equals AB plus M is 1 plus M. Therefore, R mod M is a field because every element has a multiplicative inverse. Every non-zero element has a multiplicative inverse. All right, and then we go the other way. Next, let N be an ideal of R, such that M is a proper subset of N is a proper subset of R. And then also, again, I didn't state this explicitly because I assumed that was clear from the definition. But again, he does state it explicitly in the proof in the book, so I figured I might as well do that too. Since R mod M is non-zero, that means obviously that M is not the entire set R. You need that for the definition of a maximal ideal, but I didn't think to write it because it's in the definition. But anyway, take n in n minus m, then n plus m is not equal to m, implies there is k plus m in R mod m, such that n plus m times k plus m is nk plus m equals 1 plus m, since R mod m is a field, which implies that nk minus 1 is an element of m, implies nk minus m is 1, which implies that R is equal to the ideal generated by M and N, and obviously that's a subset of N because M is a subset of sorry, the ideal M, right, is contained in N, and the element N is in N. So all, the ideal generated by N is in there as well. So R equals that ideal is a subset of N. This contradicts that N is a subset of R. Therefore, N equals R implies M is maximal. Okay, corollary 3.1 follows directly from that one. Any maximal ideal is also a prime ideal. Let M be a maximal ideal of a ring R. This is my proof. Then R mod M is a field, which implies that R mod M is an integral domain by example 2, which implies that M is a prime ideal by theorem 3.1. That's it. It's a corollary. It follows directly, basically, from what we just did. And then just a warning here, not all prime ideals are maximal ideals, though. And then we'll see that in a couple of examples in a second. All right. So every maximal ideal is also prime, but not every prime ideal is maximal. All right. So in example 6, we have an example of a prime ideal that's not maximal. For example, the 0 ideal in the integers is prime, but not maximal, since you can see that it's prime because if you take AB in the 0 ideal, that implies AB is 0, which implies A equals 0, or B equals 0, which implies A is an element of the 0 ideal, or B is an element of the 0 ideal. Furthermore, it's not maximal because the 0 ideal is properly contained in the ideal generated by 2, and the ideal generated by 2 is obviously properly contained in the integers. And same idea here, except with a more abstract ring. The ideal generated by the polynomial x is a prime ideal of the polynomials in x and y with integer coefficients, but it's not a maximal ideal. Again, we can show that it's prime. Let fg be elements of the ideal generated by x. Then fg of 0 is 0, implies f of 0 times g of 0 is 0. And since those values they give you roots, right? F of 0 equals 0, or g of 0 equals 0 implies that x divides f of x, or x divides g of x. So that means that the ideal is prime, right? And then also we can see that it's not maximal, since the ideal generated by x is a proper subset of the ideal generated by x and y, which is a proper subset of the entire ring ZXY. Okay, and that's basically the end of the chapter, but he does give us a hint as to what we'll do in the next chapter. In the next chapter, we will see that every non-zero ring has at least one maximal ideal, and therefore at least one prime ideal. But obviously, before we get to the next chapter summary, we'll do the exercise set for chapter 3. All right, so I'll stop my screen share here, and I'll see you guys in the next video, which will be in this playlist anyway, will be the solutions to the solutions to the exercise set for chapter 3. So I'll see you guys in the next. Wait, is it chapter 3 or chapter 4? I completely Completely lost my place. Is it chapter 3 or chapter 4 that we're in? Uh, Chapter 3, sorry. So we'll do the exercise set for chapter 3 in the next video in this playlist. Let me know what you guys think down below, and I'll see you in the next one. And I do have some other videos coming out in for some of the other books as well, so keep an eye out for that, and I'll see you guys in the next one.